Hello, let's continue filling in the blanks for our class worksheets or handouts. We're up to Class 19. This is conjugated dienes. It's the start of Module 8. And on page 1, we discussed a couple of conjugated molecules such as curcumin and beta-carotene. Page 1 is good. Page 2, we looked at 3 types of dienes: conjugated diene, isolated diene, and what's called accumulated diene, which is the class of molecules called allene. Looks like page 2 is all filled out as well. At the bottom of page 2, we have a diagram, energy diagram for the heats of hydrogenation. Understand that for sure. Next, we are introduced to a reaction called electrophilic addition to conjugated dienes. And it does look like in this reaction, you're going to form an allylic carbocation. And actually, you'll form several allylic carbocations in each reaction due to resonance. And we see that in problem 1 on page 3 of the Class 19 handout. All of that looks good as well to get the 1,2 and the 1,4 product. So on page 4, why is temperature such a good way to control whether you get we call the kinetic product or the thermodynamic? So just be careful. We could divide our products into the category of 1,2 addition and 1,4 addition. We could also divide our products into kinetic product and thermodynamic, but also one molecule can represent both the thermodynamic and the kinetic, or they could be 2 different molecules. And we use temperature to try to control which one we get as the major product. And I'm going to fill out the energy diagram right now for this reaction. And what do I want to do? So this is the energy diagram. For the 1,2 and 1,4 addition of HCl. Okay, we're not going to put a temperature right now. We got 2 products. If we consider these 2 double bonds A and B, this is symmetrical, meaning that regardless of which double bond you use, you're going to get the same set of products. Hopefully, you know how to determine symmetrical and asymmetrical. Another way you can think of it as is if you name it, or if you number it from either direction, or from either end, you'll get the double bonds and any substituents in the same numbering position. And if I'm going to use double bond A, let me number it this way: 1, 2, 3, and 4. You're numbering the sp2 atoms. So we could have other carbons, we could extend the chain, but the 1, 2, 3, 4 is for the conjugated diene itself. And the 2 products we get is called the 1,2 product. Okay, so double bond B we didn't touch. Okay, and again, carbon number 1 got the hydrogen, carbon number 2 got the chlorine, and that's the 1,2 product. Let me label that actually. The 1,2 product. I'm not saying if it's kinetic or thermodynamic. That is an analysis that comes later. And then we have also the 1,4 product. So here's carbon 1. 4 is way over here. And that's where the chlorine goes. So 1 still got the hydrogen. 4 got the chlorine. And there was a shifting of the double bond because this came from resonance. And we'll see an example of that when we draw the energy diagram. 1,4 product. Okay. Just give me a second. Okay. We're going to start out with the starter material. Start out down here. Plus HCl. And we'll give it some energy level. Like that. Let me find another color. Here's the E. The higher in energy, the more unstable the molecule is. And let's jump to the products. And so we notice here, I have to use some colors. Here we have the more stable double bond. Let me circle it real quick. That one there. It's di-substituted. And if it's the more stable double bond, that means it is the thermodynamic product. So thermodynamic equals more stable alkene. If you have trouble determining whether an alkene is mono, di, tri, or tetra substituted, come see me. The more substituted the double bond is, the more stable. Well, that's great. So wouldn't we always go for the thermodynamic product because it's a more stable product? Not necessarily, because we also have the product that's made faster. And if it's made faster, doesn't that have also some, wouldn't that be the major product? It depends on the temperature. So here, I'm going to label this as the kinetic product. And that is the one that's made faster. And there's no decision to looking for the kinetic product. In my class, okay, maybe in other classes there's a little subtlety, but in my class, I'm going to say that the 1,2 is always the product made faster. Okay, that's not typically the case in many classes, but in my class, we'll say always the 1,2 is the kinetic. It is the thermodynamic that could either be the 1,2 or the 1,4. And then there are other cases where the 1,2 and the 1,4 are actually identical. We know, or we hope I can tell, or we can tell, that these two are not identical. Okay? I know that was a mouthful. And so let's start out with the thermodynamic, and we'll need some space in the middle, and let's draw the thermodynamic a little bit lower, or a lot lower actually, and we have this product here. Okay? That's a thermodynamic. Dynamic. The kinetic is also lower than the starting material, but it's higher than the thermodynamic. So I'm going to put the kinetic here. This is what we have on the handout from class. I didn't fill in the middle. So the thing is this. When we grab the hydrogen, so let me draw some of the mechanism. Running out of colors. Let's see this one. Okay, we get a carbocation, and I'm running out of space. So let me draw the carbocation here. The carbocation is always going to be allylic. That is the carbon next to the double bond. But it has to be the correct allylic carbon, right? It makes sense that it's this carbon number 2. When you add an H to double bond A, you can only add it to 1 or 2. We're going to choose to add the hydrogen to 1, so that's a methyl now, and 2 is the one that's naked, so that's a plus charge. We want the carbocation in position number 2 because it is allylic, and allylic carbocations have resonance. And this is where the 1,2 and the 1,4 product come from. So here's the plus charge over there. Okay? Now, this is resonance. So there is a hybrid structure that looks like this. It's a combination. So this is a little bit trickier. The average of these two molecules is you have 1.5 bonds here and 1.5 bonds there. Do you see how I got that? You know, this bond over here, that's always a single bond. Single, single. But the bond in the middle, single, double. The average of those two is 1.5. You don't have to put charges for a hybrid structure, but I'm going to try. Partial positive, partial positive. Right? The charge is shared between those two carbons. And so the point of this is that this carbocation, these two representations, is really this. So there's only one carbocation. Okay? So let that sink in. There's only one carbocation in this reaction, but it can be represented two different ways. I say this because on the energy diagram, there should only be one carbocation. So it's 1. We don't have 2 lines, we only have 1, and we can represent it with our hybrid. It's a little bit subtle. If you remember your resonance, you can have 3 resonance structures, and it represents only one hybrid structure. So here's the deal. To get from this starter material to the carbocation, it's just one pathway, okay? So the idea of kinetic and thermodynamic doesn't happen in this first part of the reaction coordinate diagram or the mechanism. Let's take a look at the kinetic. So the kinetic is made faster, so we're going to give it a little hill and end up in the kinetic line there. That's fast because, again, the hill is pretty little. The thermodynamic in this case is the one that's made slower. So how do I represent slower? I represent it by having a bigger hill. Okay, but it gives me the product that's more stable. So how do I represent more stable? Lower endpoint. Okay, so the bigger hill, but the lower endpoint. This is what's determining the major product. If we run it at low temperatures, negative 78 degrees C, that's actually acetone plus dry ice, CO2 solid. Okay, if you want temperatures below 0 degrees, which is ice water, mix acetone with carbon dioxide, and that will create negative 78. And we'll say this one is maybe room temperature, which is around 21 degrees Celsius. The border, by the way, is 0. So that is the border between kinetic and thermodynamic, 0 degrees. Higher than 0 degrees, aim for the thermodynamic as the major. Lower than 0, aim for the kinetic. Just like the ACE problem, I will ask you to draw all the products and then circle the major based on the temperature. Now, it gets a little more complicated if we have an asymmetrical. Right now we have symmetrical, okay? Asymmetrical will have 2 different carbocations, one from A and one from B. I don't know if we get to that in this handout, but I'm good with this drawing for page 4. Okay, make sure you understand the notes at the bottom of page 4 that talk about the kinetic and the thermodynamic. Next is page 5, where we look at the top symmetrical conjugated dienes. I did leave some blank, so let me take care of that. This is in the box. Okay, so we could practice. Or, if you haven't done this yet, go ahead and do it on your own. The question is, or the problem is, draw all the products, circle the major. That's 1. And they're both symmetrical, by the way. And so, let me put here symmetrical. This is the top of page 5. Page 5 of class, what is this? Class 19. Okay. The second problem is HCl at room temperature. Okay. Draw both. Oh, let's not say both. Draw all. Circle major. Indicate or erase identical. So if you draw 2 structures, they have to be different. If they're identical, erase or tell me that they are identical. Okay, I'm going to do this kind of fast. I'm going to use double bond A for both cases. So the 1,2 is easy. Just put the bromine or the chlorine in the 2 position, right? It came from the carbocation that was allylic. Okay. Now, if you need to draw the carbocation, I mean, that's fine, but you're going to have to learn how to get to the product faster, okay? Because to to get the 1,4 product, we do resonance, and we get our second product, in this case, the bromine on the 4 position. 1 and 4. Circle the major. It's kinetic. Temperatures. Kinetic is always 1, 2, and we only have one 1, 2 product. It's this one here. Okay. Let's try to do this without the carbocation drawing. So for double bond A, right there. Now, if you had put the chlorine on this carbon, technically I can't take off points, but if I held a molecule study, you got to realize it's this carbon that's getting the chlorine. Nothing happened up here, right? Nothing happened up here in the mechanism. But technically they would be the same product, so I wouldn't take off points, but there'll be other examples where it wouldn't be the same product if you choose the wrong allylic carbon. Now look at this. When I shift the double bond in resonance, the double bond goes now here. Oops. And we could even number it. Maybe that might help. 1, 2, 3, 4. 1, 2, 3, and 4. So this is the 1,4 product. So wouldn't it make sense that the chlorine goes at the 4 position? These two are identical. And I did give a temperature, room temperature, but it doesn't matter. Room temperature would tell me the thermodynamic, but they're both the same product. You know, what I say here is that put identical. Okay, so this is a good enough answer for full credit, but the consequence is this. You get one product at any temperature. Any temp. Because the 1, 2 and the 1, 4 are identical. Okay. We do get to some asymmetrical dienes, conjugated dienes in this handout. At the bottom of page 5, I left it blank, but it is the same type of problem as the one in the box on page 6. So I'm good with leaving the bottom of page 5 blank because it's the same problem. I just changed the HBr to HCl. It's the same problem as the top of page 6, which is the box. So if you look at the box in page 6 of Class 19 handout, I drew two... Did I fill it all in? Okay. So I did not fill in everything. Let me do that for you. So this is page 6 in the box. Page 6 in box, Class 19. And I'm going to do this kind of fast. Many of you have seen me in drop-in hours already, so there's no need to belabor how to do this step by step. Okay. Let me show you how I would do this without drawing the carbocation. It's a little more complicated because I have to choose now between double bond A and B when I choose the major product. I still have to draw potentially all 4 if none of them are identical. I still have to draw all 4. But choosing the major, I have to determine which one is a more reactive double bond. Let me remind myself here that I want the kinetic, okay? But I don't know, is that the kinetic of the double bond A product or the double bond B product? Okay, so here's the deal. If I use double bond A, the two products would be this. Okay, that's the 1, 2 product. And the 1, 4. Remember, with the 1, 4 product, your double bond shifts. 1, it goes between 2 and 3. Okay, so that maybe you want to memorize that or understand that. And the chlorine now goes on 4. Okay, so that's for double bond A. For double bond B, okay, you do have to draw, looks like all 4 products. It doesn't look like any of them will be identical, but we'll double check. Double bond B, the numbering goes in the opposite direction because we start out with double bond B on the right. So that's a 1-2. Okay, you see how that's a 1-2 addition? And again, with the 1-4, the double bond shifts to the 2 and the 3 position. Okay, let me draw the rest of this. The 4 position has the chlorine. I believe none of these are identical. Definitely, this is the only one with the terminal alkene. These two have them in the middle, but this chlorine's at the end. And this one has the double bond with these 2 methyl groups. None of them are identical. So here's the analysis. Before you just circle a kinetic, kinetic's always 1-2. Okay, that's great. Find the 1-2 product. But 1-2 of which double bond? From A or from B? So I'm choosing between these two. We have to determine which double bond gave me the more stable carbocation. Now, if you recall, and you should recall, the carbocation is where the chlorine went. So I'm not going to draw the carbocations. I'm going to know that, oh, this used to be a plus charge, right? Don't do that. But I'm just showing you that used to be a plus charge. Label each carbon that used to be a plus charge as primary, secondary, or tertiary. This is secondary. This is secondary. Oh boy, this is secondary still. So we have a difference. This is primary, thank goodness. The carbocations came from 2 resonance structures. So you're averaging those 2 resonance structures and seeing which one is more stable. The more stable carbocation is the one that's made faster. And so let me write that. The more stable this carbocation, the faster. And we want the faster, okay? Regardless of whether we want the kinetic or the thermodynamic, we want the faster it's made. Faster, whichever double bond gives you the most stable carbocation, that's what we want. The faster it's made. Okay? And it's A. So A is the winner in terms of the double bond being used, and the the kinetic of the winner is this one. Okay. Do you want to try another one? Because on the bottom of page 6, I have space, yeah. Why don't you try this one and pause the video. At the bottom of page 6, class 19, I have now this asymmetrical conjugated diene. Oh man, I'm still going for the kinetic. Negative 78 degrees Celsius. Give me 1 second. I know some of you have caught a mistake. Let me just double check if the border is 0, because I'm not going to be ambiguous on your exam. Do I say the border is 0? I should say the border is 0. Okay. I'm not going to be ambiguous on the exam. On the handout, I have a 0 here. Let me change this to negative 20 degrees C. So that's kinetic, and that's this one right here, okay? I know in class that I said 0 was thermodynamic. On the exam, you will not get a temperature of 0. I'll make it very clear that it's either above 0 or below 0. Now, if you wanted, okay, I'll put this in purple. If you want the thermodynamic, so let's say the temperature is 15 degrees above 0. Okay. Very interesting. This is also the thermodynamic because that double bond is tri-substituted. It's coming from the more reactive double bond, A, and it's more substituted than this double bond here. So this tri-substituted. And so in purple, I'm also going to circle this. Okay, let me change this color to green so everything matches. My apologies, I didn't realize that I said 0 was thermodynamic on the handout. It's not. We'll say 0 is the border, and I'll make it very clear. I'll pick a number that's either above 0 or below 0. In this case, it didn't matter because the kinetic and thermodynamic are identical. They're both this molecule right here. Okay, circled in green and purple. My apologies. All right, so let's take a look at, everyone have this? Let's take a look at the kinetic. Okay, now I'm kind of nervous. I don't want to make the same mistake. This is kinetic. And we have A and B. I can't tell, honestly, which is more reactive. I wouldn't get fooled. I don't want to get fooled by this tri-substitute double bond. I need to go ahead and draw the products and evaluate from those products which one is the more reactive double bond. So double bond A, the 1,2 product, B stays there. Okay, 1,2 is right there. We can label it 1, 2, 3, and 4. Plus this here. What's naked? This carbon here. And we can verify. 1, 2, 1 got the hydrogen for sure. 2, 3, and 4. For double bond B, we have double bond A staying, and we have the chlorine here. That's the 1,2 product. Remember, we've got a number from the other side now because we're using double bond B. And we have from the resonance, give me 1 second. So here's carbon number 1 still. 1, 2, 3, and 4. 3 had a methyl. 4 now is where we put the chlorine. Okay, let me get this out of the way. Plus. Okay, we got all the correct pluses. Okay. We gotta choose the double bond that gives us the more stable carbocation. Regardless of whether we want the kinetic or thermodynamic, we always have to choose the better double bond. Man, I really hope this works. So, this carbon here, tertiary. Okay, it's connected to 3 other carbons. Carbon here, secondary. Carbon here, secondary. Okay, good. Carbon here, secondary. Just by coincidence, A is the winner again. Okay, is there a way that you could tell? Man, that's crazy. Because, look over here. A is the winner, and it's the less substituted double bond. Over here, A is the winner, and it's the more substituted double bond. So again, I cannot tell very easily just by looking at the starting material which double bond is the more reactive. Draw your products, do your analysis, okay, to find the winning double bond. Okay, let me double check because now I'm a little nervous. Why is that? It's because when up here when we use double bond A, when we shifted it, we got oh boy. I forgot a methyl group up here. Oh boy. Does it change anything? Oh boy. It's now tertiary. So, phew, it's still the winner. And so A is the winner because mainly when we did the shift, we got a tertiary carbocation right here. A is the winner here because the initial carbocation was tertiary. So, again, I cannot tell unless I draw the products and do my analysis. Okay, everyone make that correction. Whew. I'm pretty sure some of you found that. Now I'm checking all my methyl groups. 2 here, 2 here, 2 here. 1 here, 1 here, 1 here, 1 here. Okay. Yikes. The kinetic product is the 1, 2 always in our class, and it will be this one here. If I wanted to throw my dynamic, actually it would be this one. Try substituted. Okay. On page 7, which is the last page of Class 19, we will skip this semester. I'm not going to ask you to make a conjugated diene. So this was synthesis. It uses reactions from Organic Chemistry 1, but we're going to skip it. So formally, we will skip page 7 on Class 19. Oh, going a little fast. If you caught any mistakes, let me know where it is, and I'll give you a point for finding it. But I think I caught my mistakes. The temperature and the methyl groups. Yowzers. Okay. That's Class 19. Class 20 is Diels-Alder, and I'll post a video for that handout in just a bit.